Alright, I find this problem extremely frustrating, but now that I have a solution, it should be fairly straightforward. Okay, so let's start. For A, each ZIG is a subgroup of G. I use less than to be a subgroup. It could be equal to or just a strict subgroup. So I guess I really could write it like this, like they do in the problem, but my teacher did it like this, and so I kind of developed that habit. So anyways, so each of these, and thus is a P group. That's going to be important. If Zi plus 1G happens to be equal to ZIG, then 1 equals Zi plus 1G mod ZIG, which by definition is equal to the center of G mod ZIG. Which means that ZIG equals G, because G mod ZIG is going to be a P group as well. Well, it's going to be of the order P to some power, since you just divide them out. And you know that we know that the center of any non-trivial, well, the center of any P group is non-trivial, and so the only scenario is where G mod ZIG is the trivial group, which means that ZIG equals G. And thus, G is nilpotent. Otherwise, so if Zi plus 1 G is not equal to ZIG, then Zi plus 1 G contains but is not equal to ZIG. I guess you might want to prove separately that these inclusions do actually hold. You probably would do that when you first learned about upper central series, but I don't know. I didn't, because I don't know if I ever covered this in a class. I know I've covered these in like a homework problem or something, but I think we just assumed like, oh, you know that this is a series and you have these inclusions, and each Zi exists and is unique. But I mean, for me, just looking at this, it's not obvious to me that that should be the case. That's something that I should go back and prove or find a proof of, but I haven't yet. And luckily, I don't have to do so in order to do this exercise. Anyways, so otherwise, we have this. By the way, my handwriting is really bad again. That's because I'm working on writing without leaning my hand on the table. So this is going to be good for my hand, bad for my handwriting. So good for me and bad for you guys. But anyways, so otherwise, well, it's good for you guys because I can keep making videos and not have to like stop because my hand like explodes. So since G is finite, not fine, ZIG equals G for some I. Because otherwise we'd have this Zi plus 1 would contain Zi as a proper subgroup, and so the this upper central series would just get bigger and bigger and bigger, and so it would eventually grow to be the size of G. So anyways, that's part A. It's a pretty simple, straightforward argument. Okay, so now for part B. This one is tricky. Well, I don't know if it's actually tricky or if I just for some reason was not thinking well. But first, we need a lemma. First, claim that for all I, so you're greater than or equal to 1, if G is a P group and ZJG is not G for all J strictly less than I, and of course J is greater than or equal to 0, because otherwise it's not defined, then ZIG must have order at least P to the I. So you should see that this will give us, this is not going to quite give us what we need, because what we need is nilpotence class less than or equal to A minus 1, and this is going to give us nilpotence class less than or equal to A. But anyways, it's our first step. For the base case, if Z0G is not G, well, that's actually, let me just say Z0G equals 1, which is not equal to G since G is a P group. And P groups have power P to the some power greater than or equal to 1. So Z0G is this. And G is a P group. So G has non-trivial center. And certainly the order of the center of the order of the center of G must divide the order of G, which is equal to PA for some A. So this means that the center of right, so Z1G is going to be, well, that's just equal to the center of G by definition, and it must be at least P, because that's the only way for it to divide P to the A. Okay, so that's the base case. Now suppose N is such that if ZJG is not G for all J strictly less than N, then Z and G is greater than or has norm greater than or equal to P to the N. Now we're going to do the inductive step. So suppose ZJG is not G for all J strictly less than N plus 1. Then it holds for all J less than N in particular. It's kind of obvious. And so by our inductive step, we know that ZNG is greater than or equal to P to the N. See, and let's see here, since ZNG is not equal to G by assumption, we know that Zn plus 1G contains but is not equal to ZNG. And so the center of G mod ZNG is not equal to 1. So then, remember, this is G mod ZNG is again, this is a quotient of P groups, and so it's a P group, and it's not 1. So, well, it's a quotient of p groups, and then it's of the form p to the m for some m greater than or equal to 0. And of course, it's not the center of this quotient is not trivial, and so it can't be that g mod zn. Right. It's going to be, so the center of g mod zng is going to have to divide the order of this p group, which is p to the m for some m greater than or equal to 1. And so this center is going to have power p to the sum. It's going to have, it certainly is going to be greater than or equal to p. It's going to be some multiple of p, but certainly going to be greater than or equal to p. And so what do? So then we have p is less than or equal to order of g of z of g zn g, which is equal to zn plus 1. No. Okay. Zn plus 1g. No. G mod zng. And this is going to be less than or equal to zn plus 1g. This equality was by definition, and now here for this one, we use our inequality that zng is greater than or equal to p to the n. So because we're taking the inverse, we flip the inequality sign, and so we have p to the n. And so moving this over to the other side, gets zn plus 1g is greater than or equal to, right? Yeah. It's greater than or equal to p to the n plus 1 as desired. Because here we assume that, right, so we got z to the n plus 1g is greater than or equal to p to the n plus 1, and that's what we need for our inductive step, and hence it holds for all I greater than or equal to 1. So now we can move on to what we're actually trying to prove. So for the desired results, suppose a is greater than or equal to 2. Let G be a group such that the order of G is equal to P to the A. Suppose ZJG is not equal to G for all J strictly less than A minus 1. And I'll come back to this because you might be curious about that. Then, by our above result, norm of ZA minus 1G is greater than or equal to, greater than or equal to PA minus 1. So then G mod ZA minus 1G is going to be less than or equal to, well, you just break it up, and it's going to be, because everything has finite, all of these are finite groups, and so we have the order of G divided by the order of the other thing, and so the order of G is just P to the A, and the other thing we use our inequality, and it's 1 over it is less than or equal to 1 over P to the A minus 1. So this is P, and so the center of G mod ZA minus 1G. Let's see here. This is a group of order less than or equal to P. And we know that groups of order P are abelian. And so they have trivial. Right. Wait, hold on. Oh, okay, that's not a closed parenthesis. Now I'm curious about some of the other stuff I was saying about. Right, okay, so yeah, so it's abelian. Oh, wait a minute here. Wait a minute, it's abelian. It's abelian. So if it's... Oh, here's where I was confused. So if it's abelian, then this order is equal to P. I don't think this is what I want. Alright, I've got it. So, suppose G for all j less than a minus 2. By our above results, we have z a minus 2g greater than or equal to p a minus 2. So g mod z a minus 2g is less than or equal to this, and so what that means is that this quotient is abelian, and so its center is equal to the thing. So anyways, then z a minus 1 of g, the norm of z a minus 1g divided by the norm of z a minus 2g, well, that would be equal to the norm of just the quotient. And of course, the quotient here by definition is equal to the center of g mod z a minus 2g. But that happens to be equal to g mod z a minus 2g. And then you can, when you take the norm, you can break out the quotients. And so this happens to be equal to the norm of g divided by the norm of z a minus 2 of g, which implies z a minus 1g norm is equal to g, and so z a minus 1g is equal to g. Hence G is of nilpotence class less than or equal to a minus 1. Okay, now I did mention earlier that I used a minus 1, and I was going to make some note about that. What I was going to say there was that, like, I had an incorrect proof before. I completely blanked on something. And so what happened was I was saying, oh, we have to go, like, normally this proof would work for j less than a minus 2, like that this whole procedure would work, but that proof would only work if a happens to be strictly greater than 2. Because if you consider the case where a is equal to 2, then that argument you would not be allowed to apply the previous paragraph, since the previous paragraph worked for I greater than or equal to 1. But this proof, certainly if you're worried about the case of a equals 2, because technically when a equals 2, let's see, you can either think of it, the above result says if zjg is not equal to g for all j strictly less than a minus 2. And so you would say, well, let's suppose that so for the case of a equals 2, then let's suppose that zjg is not equal to g for all j strictly less than 0. Well, that's vacuously true, and so you can apply the above result. Well, if you don't like that whole, like, oh, it's true, it's vacuously true thing, then you can just look at the case of a equals 2. And when a equals 2, you have that the center of it, when a equals 2, we have a group of order p squared, which we know is abelian, and so the center is so the center of G is precisely G, and so it's nilpotent of nilpotence class 1, which is equal to a minus 1, and so you're good there. And then for any a strictly greater than 2, then obviously you can apply the previous paragraph. So I guess this, I guess this, because what was really bothering me at the end there was that thing I forgot about how centers work, which was kind of dumb of me. But, yeah, I just don't really like this. I don't find this proof very illuminating. Like, we're talking about this thing called the upper central series, and like these things are really weird because I don't know what zi looks like. Like, all I know is like, oh, you take zi to be something that does a thing, that you do a bunch of mods and you look at centers of moduli of things, and it equals module the quotient of something with quotients and centers, and it's a very weird definition. I don't see why you would think of this. Like, why you would come up with an upper central series. And it's also like, if you look at this result, like, it doesn't say like, oh, if you look at the upper central series of a group, then that will give you information about the group. What the problem says is that, like, oh, if you have a P group, then its upper central series term stabilizes, and furthermore, its nilpotence class is less than or equal to a minus 1. So what you're doing is you're taking a group and taking something that you know about the group and finding out something about its upper central series. And I don't see why you would want to know about the upper central series of a group which you already have information about. Maybe if this problem was saying like, oh, suppose that a group has an upper central series, prove that you know this about it, the group, then that would actually maybe be a little useful, because then you're like, oh, well, I don't know much about how people thought of this upper central series, but at least you can use it to learn about groups. But here, this just seems like a completely like fabricated thing that really has there's a real it doesn't I don't see any importance of upper central series here, other than that it is useful for helping you come up with problems that you can use to test students to see if they're any good at algebra. So it doesn't seem well motivated. And yeah, this is an issue that sort of comes up a lot in algebra in general, I think. Like, I see a lot of problems where it's like, oh, this problem tests your understanding of algebra, and so it's useful in that sense, but it's the result itself doesn't seem useful for any purpose. So it's sort of like, I find it hard to find the motivation to really dive into these problems if they're only useful in and of themselves, and they're not useful for helping you learn about just objects in mathematics in general. But that's just another algebra rant from me. Our actual solution probably ended like 5 minutes ago or something. So yeah, I don't have anything else to add to this proof. So we're done.